Hello everyone, welcome to the IIT-JAM tutorial number 12 in chemistry, and this is the physical chemistry chapter atomic and molecular structure lecture number 8, and today's subtopic is particle in a one-dimensional box. But before that, we have to move on to lecture number 11, tutorial number 11, lecture number 7 of this chapter, where we made a mistake. We have to make corrections to this mistake first before going on to the next lecture. So here the integrals were not having dx, so dx was missing, not only here but also here, here, here and here. So please add dx, otherwise the integrals would be represented incomplete. Okay, so the corrected form is this one. Here we have added the dx in all the integrals, number 1, number 2, number 3, number 4 and number 5. So in 5 places we have to add dx to make the correction. Now let's start lecture number 8 of atomic and molecular structure, and this is the simplest problem, the particle in a one-dimensional box in quantum mechanics. Here we have to assume the motion of a particle having mass m along a particular axis, say this is the x-axis, and the particle is confined between the walls of a container with length a. So how does it look? It looks like this. The wall of the containers from here to here, apart from distance a, so the value of x is 0. If it is 0 here, then it is a here at this point, and within this range the potential energy V is 0, but beyond these walls the potential energies are infinitely high. So the particle is moving freely in the region from x equal to 0 to x equals to a, and a is the length of the wall, length of the distance between the two walls, and from 0 to x, a, within this range, that is if x equals greater than equals to 0, or if x is less than equal to a, then the potential energy is taken to be 0, and the potential energy V is infinite if x is less than 0 or if x is greater than a. Okay, now we have the one-dimensional form of the Schrödinger wave equation, which is time independent. So let's write this equation, and from the previous lectures it was mentioned during the expression of equation number 13. So from there we have retrieved this equation here, or recalled this equation here, equation number 13, which is the one-dimensional Schrödinger wave equation, time independent. That is d2 psi dx square plus 8 pi square m by h square into e minus v into psi equals to 0. So psi is the wave function, then x is the path of the movement of the particle, and m is the mass of the particle, h is the Planck's constant, e is the total energy, v is the potential energy, and this is the Schrödinger time independent equation. And if the boundary condition in the left hand side, that is where v equals to 0, if it is applied within the box, because there within the box the potential energy is taken to be 0, then this v would become 0, so it would vanish. So it will simply become only total energy E. Okay, so this E would merge with this ratio, that is 8 pi square, it will become 8 pi square me by h square psi. Okay, so this equation takes the form like this. Now this is equation number 42, because we ended up at equation number 41 in the previous lecture. So as a continuation of the sequence of the series, it is 42. And now this is such a differential equation which is of the type d2y dx square plus ky equals to 0, and this type of differential equation has the solution y equals to a sine root k x plus b cos root k x equals to 0, and here k is 8 pi square me by h square. So the solution of equation number 42 has the form psi equals to a sine root kx, root k means root over 8 pi square me by h square, plus b cos root kx means 8 pi square root over 8 pi square me by h square, then x, and this is equation number 43, where a and b are constants. Now we are carrying forward this equation in the next sheet. Here and we have to just modify this equation according to the boundary conditions. So the first boundary condition is the value of psi equals to 0 at x equals to 0. So sin theta equals to 0 if theta equals to 0, but cos theta equals to 1 if theta equals to 0. So this cos theta value cannot be accepted as a solution of this equation, of equation number 42. And from this equation number 43, this part has to be curtailed. That means this part has to be neglected. Okay, so this would vanish. So the final form of the solution is psi equals to a sine root over 8 pi square me by h square x. But we have a condition here at the condition of the first boundary condition, which is psi equals to 0 at x equals to 0. Okay, so according to the first condition, psi can be expressed like this. That means we have vanished the second term here. So this is equation number 44. And to satisfy another boundary condition, which is psi equals to 0 also again at x equals to a. In that case, we get another expression of psi like this. Just move on to equation number 44 here. Okay, here put the value a in place of x. Okay, then it would become 0. So psi equals to, actually this is a typing error, this should be equation number 44. It can be written as, so equation number 44 can be written as, so read this as equation number 44. Equation number 44 can be written as like this. Here in place of x you are putting a, and the overall value of psi becomes 0. Okay, this is secondary boundary condition. And by solving this, sin theta equals to 0, because another its coefficient is not equal to 0, a not equal to 0, so sin theta value will be 0, and here the value of sin theta is nothing but sine root over 8 pi square me by h square a, and that value is 0. If this is 0, then what is the value of theta? So the value of theta is n pi, where n is a positive integer. Actually for sin theta it is positive with negative, both type of integral number, but here the negative values of n cannot be accepted because this is actually the quantum number. Okay, quantum number can never be negative or 0. Okay, and by rearranging this we can get the expression of energy expression. This is actually E suffix n. Okay, so you can get the value of E1 as h square by 8 square m, E2 as h square by, well, that means 4h square by 8 square m, E3 9h square by 8 square m. So this way, this is actually the expression of energy. We are writing it here as E, but actually this is En. Okay, but for simplification we are just expressing it as simply E. So energy expression we have obtained here as equation number 46, and n is the quantum numbers of the different energy levels. So let's block this, and here is the description of this equation number 46. So equation 46 is the energy expression for a particle in a one-dimensional box for different quantized energy levels, where n is the quantum number. Now putting the value of E as obtained from equation number 46, what we have obtained in equation 46. So this is equation number 46, equals to n square h square by 8 a square m. We have to put this value in equation number 44. So this is equation number this is equation number 44. Just put the value of E here. Okay, this is equation number 42. So what we have got here, so we have to write psi equals to a sine root over, within this root over 8 pi square m by h square into the value of E, and outside the root over you have to put x. Okay, so let's do this here. So psi equals to a sine root over 8 pi square m by h square. In place of E we are writing the value of E as obtained from equation number 46, and the value of E is n square h square by 8 a square m, and outside the root over it is x definitely. Now this psi like E also can be written as psi n, that is as a function of the quantum number. Okay, so for our simplification we have just simply written this as psi, but this is actually psi n. Okay, now simplify this form here. What are cancelled? H square are cancelled, then m are cancelled, 8 are cancelled. So what is left behind? What is left behind is n squared, pi squared, and well, that's all. H square cancelled, and in the denominator only a square is left. Okay, so n square h square by a square, and its root over is nothing but nh by a. Then nh by a, I'm sorry, extremely sorry, it is n square pi square. H square cancels, so n square pi square by a square, and its root over is n pi by a. Then this x merge with that n pi by a to become n pi x by a. Okay, so the final form of psi n or psi is a sine n pi x by a as a function of x as a function of n as well. This is equation number 47, and the graphical plot of this equation number 47, not only equation number 47 but also for equation number 46. 46 is having the energy expression. So we have to plot energy in the y-axis and in the x-axis the particles movement. We have graph, okay, because here in the solution of psi we have sine theta. So you have to you have got here sinusoidal graphical plot. Now these points where they cut the x-axis is the nodal point. Okay, so these are the nodes. So for n equals to 1 there is no node, but for n equals to 2 there the number of node is 1. For n equals to 3 the number of node is 2. N equals to 4 number of node is 3, and so on. And since it is psi n, so when n equal to 1 it is psi 1, for n equals to 2 it is psi 2, and so on. Okay, and the corresponding energies are obtained from equation number 46. So this is the energy, and this is the x-axis, and these are the different quantum numbers. Okay, so this is the graphical plot for a particle in a one-dimensional box. So we have to mention the dots in the graphs are the nodes, and the number of nodes are simply n minus 1, because for 2 it is 1, so it is 2 minus 1. For 3 it is 2, so it is 3 minus 1, 4 minus 1, and so on. Therefore for n equals to 1 nodes equal to 0, for n equals to 2 nodes equal to 1, and so on. Okay, now the probability distribution function is psi squared. That is the probability of finding a particle. Okay, so if psi is squared, then the value of psi squared becomes a squared sine square n pi x by a. Okay, this is the expression of psi, a sine theta, so it becomes a sine square theta. Likewise it is a squared sine square theta, so it is a squared sine square theta. So the value of theta is n pi x by a. And this equation number 48 has the graphical presentation like this. So this is the graphical presentation of psi squared as a function of x and is n as well. And the value of energy according to the equation number 46, what was there in the equation number 46? It was En equals to n squared h squared by 8 a square m. So there we can conclude that the value of energy is directly proportional to n squared, and it is inversely proportional to a squared. That means if the quantum number increases, then the energy would increase, but if the length of the box increases, then the energy would decrease. And the lowest energy, by putting n equals to 1 in that same 46 number equation, you get the energy expression E1 as E1 equals to h squared by 8a square m. For simplification, we are just simply writing it as E instead of E1, and this is equation number 49, and this energy is known as the 0 point energy. This is the lowest energy of a particle in a one-dimensional box. Now determination of the normalization constant. So there had been two constants a and b, out of which a was accepted, and a is known as the normalization constant. And here the probability of finding a particle in a one-dimensional box is psi squared dx, and this is 1 between the range within the box. That means where from x equals to 0 to x equals to a, within this range it is 1. So we can easily represent this as a form of an integral as integration 0 to a psi squared dx equals to 1. So putting the value of psi squared from equation number 48, what we get? We get this is the expression of psi squared from equation number 48. This is a squared sine squared theta dx. Theta value is n pi x by a, and this is equal to 1. And this has the solution a squared. This is the constant, and this is the normalization constant, what we are going to determine the value. and here the result of the integration is a by 2 within this limit range, and this is equals to 1, so giving the result. So here we have shown this, that the integral 0 to a, the value of integral, the integral is 0 integration d0 to a sine square theta dx. The value of theta is n pi x by a, and this is actually x by 2. So from the limit 0 to a, the value should be simply a by 2. Okay, and by solving this we can get the value of the normalization constant capital A equals to 2 by a to the power half. That means 2 by root over 2 by a, and this is equation number 50. Okay, up to 49 it's 50, and thus we get the complete solution of the problem of a particle in one dimensional box. And the energy expression En is actually, for simplification we are writing it as E, and this is nothing but as a function of n, En, it is n square h square by 8a square m. This is equation number 46 we have already obtained, and here we get another new equation. In place of a, we get the expression of psi, that is psi equals to root over 2 by small a sine n pi x by small a. Okay, so this is 50, equation number 51, and this is about the problem of particle in a one-dimensional box. This is the energy expression, and this is the wave function. Now move on to the questions. We have to find the normalization constant A if the wave function is like this: psi as a function of phi, the normalization constant capital A, then exponential IMF, where I is the complex number, and the range of phi is 0 to twice pi. So here these are the options, and it came in 2007 IIT-JAM question. So if psi is this one, okay, then what about its complex conjugate? The complex conjugate must be minus I in the power of exponential. So if psi as a function of phi is a e to the power im phi, then psi star phi must be equal to a to the power a into e to the power minus im phi. So the normalization constant, the range should be 0 to 2 pi, then psi star d phi equals to 1, but the value of psi is this one and psi star is this one, so this multiplication gives the result 1, and only a squared here remains uncancelled, so it is nothing but equal to a squared integration 0 to 2 pi d phi, and this is nothing but equals to 1, and by solving this we get the value of normalization constant capital A equals to 1 by root over 2 pi. So option A is the correct answer. And this is the next question, question number 32. The potential for a particle in a one-dimensional box is given as Vx equals to 0, and while 0 is less than equal to x less than equal to L, here instead of small a we are writing L, capital L here, and the conditions are same as usual, but you have to find the locations of the internal nodes of the eigenfunctions. Okay, and here is another thing given: m is an integer such that it is less than n but greater than 0. Okay, these are the options. It came in IIT-JAM 2022. So let's find out. This is the expression of energy as a function of x, and these are the number of nodes, isn't it? So this was the picture, but in place of a we have written it here capital L. Okay, so for n greater than equal to 2, that means we have to start from here. This is n equals to 2, and here n is greater than 2. So for n greater than equal to 2, n can have the values 2, 3, 4, etc. Now for this condition where m is also another integer and it is less than n but greater than 0, in that case for n equals to 2, m must be equal to 1. Okay, and in that case x, it is lying at half distance of L, so it is half L. Next problem is for n equals to 3. This is n equals to 3, and it is 1/3 and 2/3 distance of that box. The nodal points are lying, so x is, m is actually following this condition. If n is 3, then m can be 2, 1, but cannot be equal to 0, so it should be only 2 and 1. That means m equals to 1 and 2. For 1 it is 1 by 3, for 2 it is 2 by 3. So the value of x should be 1 by 3 into L and 2 by 3 into L, and this satisfies this result. Similarly, for n equals to 4, m can have the value 1 to 3 by satisfying this relationship, this condition, And similarly, the values of x should be 1 by 4 into L for m equal to 1. For m equals to 2, it is 2 by 4 into L, that means half L. And for m equals to 3, it can have the value 3 by 4 into L. That is, this is 1 by 4 L, this is half L, this is 3 by 4 L. Half L can also be written as 2 by 4 L also. So this is here nothing but x equal to m over n into L. So this is the correct answer. Option B is the correct answer. So that's all about this topic, particle in a one-dimensional box. Thank you and have a nice day.